In section 2, we're going to start learning some of the rules for derivatives that we can use instead of the formal definition, which takes quite a bit of time. The first two rules are really the most important and we can use in combination with a lot of other rules. So the first one talks about the derivative of a constant. The derivative of any constant is always 0, always. So if I have f of x equal to, say, 4 or pi or 7, any number, then f prime of x is just 0. Now, the even more powerful rule is the derivative of a power function. So the derivative of a power function, x to any power, can be defined by n x to the n minus 1. Now, this actually has a wide variety of applications. If I have, say, x to the 4th, then f prime of x is going to be 4. So you take the old power out front, and then you have x, and then you have one less power. That's always how you do a power function. You could also do it on things like this, f of x equals the square root of x, because the square root of x, if you recall, is just x to the 1/2 power. So if I take the derivative, I'll take the 1/2 out front, and then I'll have x, and then I'll have it to the 1/2 minus 1 power. Well, 1/2 minus 1 is negative 1/2, which is the same as 1 over 2 x to the 1/2 power. Because remember, a negative exponent flips to the bottom, so that finishes out to be 2 square root of x. So anything that's not an exponent of 0, you can use this rule on. We have a constant factor rule. This just says if you have a constant in front of a function, you can do the constantly separate from the derivative. So if I have g of x equals 7 e to the x, then g prime of x is just going to be 7 times whatever the derivative of e to the x is, which we don't know yet, but we will eventually. And then the sum and difference rule. So if I have a couple different of these, if I have a couple different power functions or a couple different constant functions, I could just take them and take their derivatives separately. So an example of that would be if I have some polynomial function, 2x squared minus 7x, well then I could just take the derivative of each of these separately. So f prime of x is going to equal 4x, because I bring the 2 down, it'll multiply with that 2 out in front, to the power of 1 minus 7x. Now you bring the 1 down, it's still 7, and it's x to the 0, but remember anything to the 0 power is just 1, so this is just negative 7. So this is much, much, much more efficient than using our long formal definition process. Let's look at some examples using the rules we just learned. So this first one should be really, really simple. It says find the derivative of negative 89. Well, there's no x, so that just means this is a constant. So remember, the derivative of any constant is just simply 0. Now the next one is y equals x to the 9th. So if I want to find dy dx, so remember, in a power function, we take the exponent down, we have our x, and then we use one less power. So 9 minus 1 is 8. All right, same thing for this one, for f prime, or f of r, f prime of r. Now a little different in this case because we have the fraction out front, so we'll take that out front. So we'll have 2/9 times the 5, because that 5 comes out front, and then r to the 5 minus 1, which is 4. Now to multiply that, I'll just multiply, it's like 5 over 1. So I'll make it 10 over 9, r to the 4 is f prime of r. Now this one looks, it's got that square root, so you might think you have to do a different power, but really, the root 5 is just a constant. But I have to write it as x to some power to use this rule. Well, if you have something on the bottom, you can take it to the top and make it negative. Just like if it's negative on the top and you take it to the bottom, you can do this as well. So now we have it in the right form. So now we can take this negative 3 down. So y prime is going to be negative 3, square root of 5. I just like to put it in front of the square root. And now it'll be x, so if I take one power away, it goes to negative 4. Now the way we typically write it is we brought it up to take the derivative, but now we'll take it back to the bottom for our final derivative. So it's going to be negative 3 radical 5 over x to the fourth. So again, the key is always to get it to be x to some power. Once it's x to some power, we can use the power rule and the constant rule to do these kind of things. So let's look at this one. So this one is y equals negative 12x6 plus 2x47 minus 4x plus 6/7 to the 93rd power. So dy dx, so I'll bring the 6 down. So negative 12 times 6 is negative 72, and it'll be x to the fifth, because again, we're always reducing by 1 power. Here we'll take the 4 down. Now it's going to multiply to the 2 over 7, but really it's just going to multiply to the 2, because it's 4 over 1. So 8/7 x to the third. Now in this case, it's the 1 that comes down, which will remain it as minus 4. And then remember, if it's just x, then it's 1 minus 1, so it's x to the 0. So there's just no x. And now this thing looks like a lot of people will want to take the 93 down and all that stuff, but this is just a constant. There's no x. So if there's no x and it's just a number, the derivative is 0. So this is my derivative. Now here's another crazy one where we have to rewrite it because it's not q to a power. Now it's got the square root in the 7, so if I want to rewrite it so I can take the derivative, so the 7th power is already there, and a square root is always a half power. So you could actually write this as q to the 7 halves. Whatever is the number on the bottom is your index of the root, remember? So if it's a cube root, that's a 3. If it's a 4th root, it's a 4. And then the 7 is just the power you see. And again, this is just algebra, no calculus here. So p prime of q, I'll bring the 7 over 2 down front, and it'll be q, and I'll actually write it out. It's 7 halves minus 1. Now to subtract fractions, though, of course, this will have to be 2 over 2. So p prime of q is going to equal 7 over 2 times q to the 5 halves. If you want to rewrite it, you could write it as 7 halves q square root of q, because the bottom number is square, and then q to the 5. These are equivalent expressions, and that's the derivative of radical q to the 7th. All right, so let's look at g of t equals negative 3 over 7x. Now again, we have the same problem. We do not have x to a power. The x is on the bottom. It has to be some number times x. So I'll bring that up. So this should be x. This is g of t. So g of x is going to be negative 3/7 x to the minus 1. There's no power, but when I take it up, whatever power there would have been, it becomes negative. So now for my g prime of x, I'll take the negative one up front. So that'll be positive 3/7, because negative 3/7 times negative 1 is 3/7. X to the minus 2, because it was negative 1 minus another one, and he's negative 2. And then if I want, I can take this back to the bottom. So it's going to be 3 over 7x squared. Now most of these on this page are ones we could have done using the long rule, but you can see it's much, much shorter to do it this way. Now this final one is trouble, because in this case we have 2 of them that are multiplied. Now, if we go back to our rules, I had rules for adding. I did not have any rules for multiplying or dividing. There are rules, but we don't know them yet. So if we're going to do this with the rules we have right now, we cannot do it this way. So what we would have to do is we would have to FOIL it together first. So this is 6x squared minus x minus 2 if I just FOIL it, and that's just doing your first, outer, inner, last. Then it's just a polynomial, which is very easy to take the derivative of. So f prime, we're going to take the 2 down, so it's going to make it 12x to the first. Now remember, this is x to the first, so we take that down, so that's minus 1, x to the 0, so it's just negative 1. And then this is a constant, so that just goes away. So f prime of x is 12x minus 1. All right, now if we look at this one, s of y equals 2y squared plus 3y minus 5 over y. Now this is division. We also don't have a rule for division. So what we'll have to do is we'll have to rewrite this. So what I would do is I would just divide them all by y. So we get 2y squared divided by y plus 3y divided by y minus 5 divided by y. And I can do that as long as there's a single thing on the bottom. So this becomes 2y plus 3. And then I'll write this as 5y to the minus 1 using that same strategy we used before. So now s prime of y is going to equal 2, because the 1 goes and becomes 0. 3 goes away, and this will become plus 5, because I'm bringing the minus 1 down, y to the minus 2. And then if I want to rewrite it, I would write it as 2 plus 5 over y squared. All right, let's look at this next one. Very similar kind of idea. We'll rewrite it first by rewriting them over w to the 4. Always trying to get it to be a variable to a power. So if I simplify, this is going to be 1 over w cubed, because you can cancel one of those with one of those, plus 6 over w to the 4th. Then I have to take them up as negative exponents, so this one will be w to the minus 3 plus 6w to the minus 4. So now I'm ready to take my derivative because I have it in the right form. So this is going to be negative 3, bringing that down, w to the minus 4, because minus 3 minus 1 is minus 4. Minus 24, because I'm multiplying that to the 6, w to the minus 5. So p prime of w is negative 3 over w to the 4th minus 24 over w to the 5th. All right, let's look at one more kind of derivative where we're rewriting the rules and stuff. So this one has a power and a negative exponent. So if I was going to rewrite it, I would rewrite it as y equals x to the 5/3 because it's cube root. And since it's cube root, that's going to be a 3 on the bottom. And this is going to be plus 2x to the minus 2. So now we have y prime equals 5/3 x. Now I'm doing 5/3 minus 1. So I'll just rewrite it, and we can look at it here in a second. And this is going to be minus 4 because you multiply that to the 2. X to the minus 3. So now if I subtract it, I get 5/3 x to the 2/3, because again, this is 3 over 3. And this would be minus 4 over x to the 3rd. If you want to rewrite it as a root, you certainly could. It'd be 5/3 cubic root of x squared, because again, the index of the root goes on the bottom of the fraction, minus 4 over x cubed. So we can also do some problems where we're finding the equation of the tangent line. We just have a much, much simpler way to find the derivative now. So let's look at this one. So let's find the derivative of this function. So we'll bring the 2 down. So negative 4 over 3 x to the 1st plus 1, that's my derivative. And we're trying to find the slope of the tangent line at 1. So we have our derivative now. Now the one thing we don't really have to get started, we know 1, but we always need a y value to go along with this as well. So we're going to have to plug 1 into our function at some point to get the y value, so I'll just do that now. So it's going to be negative 2/3 times 1 squared plus 1 minus 5. That is going to be 1/3 minus 5. That's going to be negative 14 over 3. So that's just plugging a number in and getting your point into your original function. And now we have our derivative. So with that, I'll find the slope of the tangent line, and I'll do that by plugging in 1. So that's going to be negative 4/3 plus 1, which is negative 1/3. So now I'm trying to find the equation of a line with this slope and this point. So the only thing different from what we did in section 1 is now we have a much, much quicker way to find the derivative. So now I'll do my y equals mx plus b. So that's going to be negative 14 over 3 equals negative 1/3 times 1 plus b. And so I'll add 1/3 to both sides. So that's going to yield that b is going to be negative 13 over 3. Now, that's fine. I have the slope, I have the intercept, but now I have to actually write my line. Y equals negative 1/3 x minus 13/3. Now again, just like we did when we did the formal definition of the derivative, if you graph your original function, this quadratic function, some kind of parabola, and then you graph your tangent line, it should meet at one spot right on the edge of that graph. All right, let's look at one more, kind of a similar kind of problem. So we have y equals 2 over x at x equal negative 1. Now this one's a pretty easy one to get the y value. You just plug in negative 1, so you get negative 2 over negative 1, which is just 2. So my point is negative 1, 2. So now I'll find the derivative, and this is one where I have to rewrite. So it's going to be negative 2x to the minus 1, same thing we talked about. So y prime is going to be 2x to the minus 2, because I take the negative out front, take one less power. So that's 2 over x squared. That's my derivative. So my slope of my tangent line, I'm going to plug in negative 1 to this. So I'm going to get 2 over negative 1 squared, which is just going to be 2. So I've got my point, and I've got my slope. So now again, I'll find my y-intercept. Y equals mx plus b. So we have 2 equals 2 times negative 1 plus b. That's 2 equals negative 2 plus b. So b equals 4. So my tangent line equation is y equals mx plus b. So again, if you graph negative 2 over x and you graph this line, you should see it tangent at that point negative 1, 2. So all the rules we've learned so far are kind of dealing with polynomials and power functions. We've extended them to roots and things like that by kind of making them fractional powers. But there are also derivatives you can do for sine, cosine, tangent, and things like that. Now, these are pretty steadfast rules, and we'll learn the other trig functions later. But the derivative of sine x is always cosine x. So the derivative of sine always becomes cosine. And the derivative of cosine becomes negative sine. So they're not quite the same. They're not derivatives of each other. Sine is cosine, but cosine is negative sine. So if I look at problems like this, so if I have y prime equals negative sine theta equal over 4, well, remember, this is y equals basically negative 1/4 sine theta, because I can rewrite the 4 as a fractional constant out front. So if I do dy d theta, the derivative of y with respect to theta, it would just be negative 1/4 cosine theta, because constants out front don't change. And then the derivative of sine is just cosine, so it would just be this. So that's a pretty nice rule. Now the second one you see here, the sine and cosine are not a problem, but we have to rewrite that first part, because this goes back to what we did earlier. So I would have to rewrite this as 3x to the 4/3, and then everything else would be fine. It's 2 sine x minus 3 cosine x. And again, no calculus has been done yet. I just rewrote it. And so now I can take the derivative. So f prime of x is going to equal 4/3 times 3, because I bring that 4/3 down, and it'd be x to the 1/3. You'll notice these 3's cancel in this one. And the next one is sine. Well, the derivative of sine is cosine, so this just becomes 2 cosine x. That doesn't change the number out front. This one is negative 3 cosine, so this will change to positive 3 sine x. Reason being, remember the derivative of cosine becomes negative sine, so you have negative, negative sine. So our final answer, f prime of x, would just be 4x to the 1/3, and you could write as cubic root of x if you want, plus 2 cosine x, plus 3 sine x. So we're just taking each of these longer problems and breaking them into their little parts. And really the only derivatives we know so far is that power rule and sine and cosine. So the last really basic derivative rule we can do is for an exponential function, and this is like the coolest function in math, and it's just for this reason. If you have your exponential function, e to the x, and remember e is that special base of the natural logarithm, it's that special Euler number, 2.71828. Well, if you take the derivative of e to the x, you get e to the x. The magic thing about this function is it is the derivative of itself. So if I wanted to take the derivative of 6e to the x, I'm not going to make that negative x because that's a little past where we are right now. Then f prime of x would be 6e to the x. It doesn't change. It's the exact same. Now this next one, if I do f prime of t, the e to the t over fourth doesn't change, just stays the same. Now the 8 cosine t will change. It becomes minus 8 sine t, because remember the derivative of cosine is negative sine, so you get that negative out front. All right, so hopefully you'll like these rules. We will practice them a lot, and they will become like second nature.